Okay. Okay, can we start?
Yes, you are live.
Okay, nice. Hello, everyone. Welcome to the fourth session of the seminar in computer architecture. Today, Jan is going to present a nice paper about critical path prediction, which actually many papers have been inspired by this work. Jan is the fourth semester of computer science, and he is interested in computer architecture and low hardware design. So yeah, basically he's interested to present this talk, and we wish you good luck.
Thank you, Mohammed. Yeah, I want to take this moment before I start to thank my mentors too. They had really suggestible notes and pointers that really helped me prepare this presentation. Okay. Yeah, so today I'm presenting the paper focusing processor policies via critical path prediction. It was presented at the International Symposium for Computer Architecture in 2001 by these three researchers, Brian Fields, Shai Rubin, and Rastislav Bodik from the University of Wisconsin-Madison. I'll jump or not. Okay, I can't skip the slides. Okay. Okay, great. All right. What is happening? Okay. All right. All right. Okay, let's go. We'll start with the executive summary. So the motivation for the work in this paper was that at the start of the 21st century, the out-of-order processors became increasingly sophisticated, and there was increasing amounts of parallel processing in the CPU. So you would have to start thinking about the critical path of a program, which is the path that defines the overall execution time. And the idea they had was to predict whether an instruction is on that path so they can prioritize it for policies that the CPU applies. Because up to then, the CPU applied all policies in an egalitarian way. It was unaware of the criticality and relevance for the runtime of individual instructions. And the challenges they had was that the compile time optimizations only considered data dependencies, and they say and show that that is not precise enough to determine a critical path. And when you want to do it in hardware, as they do, you have the additional challenge that the processor only ever sees a fraction of the code, while you want to optimize for a global critical path. So the question is, how do you find the critical path globally if you only see a fraction of the code? The key mechanism they came up with is a token passing algorithm that estimates the criticality of the nodes. It's a bit cryptic right now. It will get much clearer, I hope, later on. And they showed that with the mechanism they implemented, the scheduling could be improved and improve the CPU performance as well as prediction. Those were the two applications they examined in the paper. This is how I'm gonna go through the paper. I'm gonna discuss the sections, the model of the critical path, how they predict the critical path in hardware, and then the applications I just mentioned. I'm gonna conclude, analyze the paper, its strengths and weaknesses, and then we'll have a nice discussion. So I mentioned the compiler model of a program. So you can see here we have some assembly code. It doesn't do anything particularly interesting. And what the compiler does is it optimizes the execution of the code by analyzing which instructions are data dependent on each other. So it has these instructions 1 to 10, 0 to 10 actually, that you can see here, and then it looks which instructions produce operands for the following instruction, and then you get a dependence model that you can see here. The problem with this is that it only looks at data dependencies and it doesn't capture a lot of other dependencies, such as control dependencies. For instance, if there's a branch and it mispredicts, you have to flush the pipeline, and the additional latency that comes with that is not captured. You have in-order dependencies. We're going to be looking at out-of-order execution machines, but they still dispatch in order and also commit in order, and that produces further dependencies. And you also have reorder buffer limitations, which I'll explain later on. So what the researchers did, they expanded the critical path model from the compiler, or if you could call it critical path, what the compiler did, but they expanded the model, and now they aim to model the critical path. And you have, for each instruction, you have the execution nodes, you have the dispatch nodes, and you have the commit nodes of each instruction. And with all of these nodes, also come new dependencies. Yeah, it's a bit overwhelming right now. I'll explain what the individual edges are. So you first, you have sort of trivial dependencies. You can't execute before you dispatch, and you can't commit before you execute an instruction, which is pretty obvious. And you also have, like I mentioned previously, you have in-order dispatch and in-order commit. So that's also dependencies that appear. Then you have the data dependencies, which the compiler already captured. And now it gets a bit more interesting. You have also the dependence which is created by the limited size of the reorder buffer. You can't dispatch instruction 10 before instruction 6 is out of the reorder buffer, because the reorder buffer is full at that time if instruction 6 is still in the reorder buffer. So that creates another additional dependency. And you also have control dependencies, which I previously mentioned. So if instruction 7, which was a branch instruction, mispredicts, that creates additional latency, and that is captured by this edge here, which goes from E7 to D8. And you also have weights. Those are the latencies it takes to resolve the dependencies. The great thing about the weights is that you don't have to calculate them. You can observe them in the simulation they run, and then later on at runtime too. So that's great. It doesn't add any further complexity to the model per se. And then when you have that complete model, you can also find the critical path, which is simply the path from D0, from the dispatch node of the first instruction to the commit node of the last instruction. And the critical path is simply the path with the heaviest weight that leads from D0 to C10 in this case. Right, and then you can also see the critical instructions, which are instructions that have nodes that lie on the critical path. So we have this model, we can find a critical path in it. And now the question is it any good? So what they did to determine whether the model is good is they ran simulation with 12 different workloads, I think, and established a baseline. And when running the simulations with these workloads, they built the critical path graph from the simulations. And then they knew which instructions were critical and which weren't. So they did the following comparison simulations. They now decreased the latencies that were on the critical path by 1. And in another simulation, they decreased the latencies of the non-critical path instructions also by 1, and they compared that to each other. And the idea was that if a latency it comes from an edge on the critical path and we reduce that latency, that should reduce the overall runtime too. And on the other hand, if the edge is not on the critical path, it shouldn't do much to the runtime because it wasn't defining the overall execution time anyway. So you can see here the first evaluation they made. You can see the improvement is measured in execution time reduction in cycles per cycle of latency reduced. And you can see that when reducing the critical path latencies, you had a pretty high ratio of reduction for the critical path latencies, while reducing non-critical path latencies didn't do much at all. You can see that the authors conclude then that the model is pretty good at identifying critical instructions. And what also comes with that is a pretty nice insight, at least what I thought, is you can see these ratios of reduction per cycle. And what that also shows is how dominant a critical path is, because once you've identified the critical path and start reducing the latencies, it could happen that if you've reduced the latencies enough, that another path that you did not identify as critical is now critical. And after that, the latency reduction won't do much for the path you identified. And they also did a second evaluation where they just broke down the criticality of instructions per workload. And what's important to note in this graphic is that overall, there aren't much critical instructions. It depends per workload, but on average, there aren't a lot of critical instructions. And specifically, only 2 to 13% of the instructions were execution critical. And that goes to further show that what the compiler did, looking at execution dependencies coming from data, cannot be enough because it only captures 2 to 13% of the overall instructions. So now we have the model. We know it works well enough, and now we want to know how we implement it in hardware. And to do that, the authors came up with the last arriving rules, and they observed that the critical path can be computed solely by observing the arrival order of instruction operands. And for that, they introduced the notion of last arriving. And last arriving means if you have a dependence between a node I and the node J, a node I comes before J, and it is the last to be resolved for node J, the according edge from I to J is called last arriving. And they also observed that each edge on the critical path is last arriving. And if an edge is not last arriving, it can't be on the critical path. So in the simulation, you can build the critical path pretty easily with these last arriving rules. You start at the commit node of the last instruction, you traverse the graph backwards along the last arriving edges, and you're done when you arrive at the dispatch node of the first instruction. You can see here the model, the previous model with the not last arriving edges, and then the last arriving edges, and then we're going to fill in the last arriving critical edges. And you can see, for instance, here, each node only has, well, you can't see that online, I'm sorry, but I'm pointing at commit node 10, which has the last arriving edge coming from E10 and so on. And obviously each node only can have one last arriving edge. And then you start at C10 and you trace back along the long last arriving edges, and you go through the graph, and you can build the critical path like that pretty easily. Now the problem is this approach works for simulations, but if you want to do it in hardware, it's pretty expensive because you would have to save the entire graph, you would have to save the nodes and which nodes are dependent on which nodes, and also the backwards traversal wouldn't be trivial to implement in hardware. So now the authors came up with what is the key mechanism of the whole paper, which is really the nice idea they had, which is the token passing critical path predictor. So they don't set out to capture the exact critical path, but they aim to predict and approximate it. And the intuition behind their idea is that the critical path, as you previously saw, is a chain of last arriving edges through the entire graph. And if you're the processor and observe a long chain of last arriving edges, it is likely that this chain of last arriving edges is part of the critical path. And this chain can be found with forward propagation of tokens at runtime. I'll explain that in the next few slides. And the great thing about that is that it doesn't require any graph building at all, because you can only look at the nodes and the arrival order of the instructions, of the dependencies. I mean, so you don't have to keep a graph. It gets more clearly in the next few slides. The algorithm goes as follows. You plant a token at the node n of which you want to predict the criticality. Then you propagate the token forward along the last arriving edges. And if a node doesn't have an outgoing last arriving edge, the token dies. After allowing the token to propagate for some time, you check whether the token you planted is still alive. And if the token is still alive, you train the node as critical, and other ways you train the node as non-critical. I have visualized this with an animation, so it's a bit easier to understand. Now we want to predict whether node C3 is critical. So we plant a token, and you can see node C3 has 2 outgoing last arriving edges in bold black. And when you have multiple outgoing last arriving edges, you just multiply the token. So the token travels from C3 to C4 and D7. And the same thing here. We have last arriving edges that are outgoing, so we propagate further and further. And now you can see C6 and C7, they don't have outgoing last arriving edges, so the token doesn't get propagated further, but it gets propagated from D8 to D9 and E8. So now we've propagated for some time. We check if the token is still alive. It is still alive. So we predict that C3 is critical to the overall execution time. For the concrete hardware implementation, you have a critical path table that is indexed by the program counter of the instruction. That's pretty straightforward. You just have a table with all the instruction counts and a prediction whether they're critical or not. And then the trainer is implemented as a small token array. And here comes into play what I talked about earlier about the reorder buffer size. I explained to you that there isn't any dependence that, what I meant to say is you have the reorder buffer size and you can't have any dependence that is longer than the size of the reorder buffer because it would have already been put out of the reorder buffer beforehand. And already completely computed, so there can't be any dependence ranging over the size of the reorder buffer. So we can also limit the size of the token array to the size of the reorder buffer, which is pretty convenient if you want to keep hardware cost low. And then they had these training parameters, which they used to train the criticality of the nodes. They stored 16K, the criticality of 16K entries, 16,000 entries with a 6-bit hysteresis. They had a token propagation distance of 500 plus the size of the reorder buffer. They had multiple tokens in flight at the same time. They allowed up to 8 tokens. And the hysteresis, they went with is pretty leaning towards predicting critical. And then there's also the token planting policy you have to think about, and where they decided to plant the token randomly within the next 10 instructions when it comes available. And now they went on to evaluate the critical path predictor. They did a comparison where they compared the predictions the critical path predictor made to the ideal critical path that they would observe in the model. And then they also introduced a comparison against two heuristics, which were commonly used back then, the oldest unissued or not commonly used, I said, but were used to sort of gauge criticality of an instruction. And there's the oldest unissued instruction, which just marks an instruction as critical if it's the oldest unissued instruction every cycle, and the same for the oldest uncommitted instruction each cycle. And then you can see the results here. You have the 3 bars, the oldest uncommitted, oldest unissued, oldest token passing algorithm, and you can see that it's very accurate at predicting the criticality. It's up to 88% and with an average of 80%, which is pretty good. And it is especially good at correctly predicting the critical instructions, which you can see with the incorrectly predicted non-critical part, which on the third bar for each workload is very tiny for the token passing predictor. So it doesn't miss a lot of critical instructions. And then to have an evaluation independent of the model they established, they also compared the speed up directly to the heuristics. And you can also see here that the token passing algorithm fares pretty well. While a heuristic may work nicely for some workloads, the key strength of the predictor is that it's very robust, or that it's very robust across different workloads. All right, now we have seen how they model the critical path, how it is implemented in hardware, and now we want to talk about some applications, or about two, which is the focused cluster instruction scheduling and steering. And they also discuss focused value prediction in the paper, but I'm going to focus on the first bullet point here. So what does that mean? Or why do we need it? The out-of-order processors are becoming increasingly complex. So there are proposals to cluster the instruction window and have different clusters with their own functional units that can process in parallel. And you, of course, have to schedule and steer the individual instructions towards these different clusters. But there are challenges that come with that. You have, for one, the latency to bypass results is increased, because now if you have a result ready and have to bypass it to a completely different cluster, that's additional wiring and that's additional latency. And what we use for that is instruction steering. And then you also have functional unit contention that is increased because the issue width for each cluster is smaller. And when the load balancing is off and a lot of instructions get scheduled for one cluster, then you have a lot of contention for a smaller issue width. And even worse is that if you want to combat these problems, that the steering policy and the scheduling policy have conflicting goals, because if you have good load balancing, you have a lot of distribution over the clusters, so the bypass latency is increased. But if you schedule the instructions within the same cluster, there's a danger of increased contention. So they modified both those policies. I'll start with the steering policy. The baseline is which they compared their improved policy to, is the register dependence steering. And what the idea is here, that you assign instructions to clusters that produce their operands. So you don't have to bypass the result to different clusters. And if there's more than one producing cluster, if there's operands distributed around about the different clusters, then, which is called a tie, then you just choose the cluster with the fewest instructions. And the authors modified that policy slightly. They modified the policy for the tie. If you have a tie and the instruction you have to steer is critical, it is placed into the cluster of its critical path predecessor. So you keep the bypass latency along the critical path low. And that is okay, because if you prioritize critical path instructions over non-critical path instructions, it doesn't hurt much the performance, because if the latency is increased for the non-critical instructions, you shouldn't have an effect on the runtime immediately. And then we have to deal with the increasing functional unit contention. And the baseline policy for that is they just prioritize instructions where we know that they have long latency. And the modified policy, the policy they implement with the critical path predictor, is that they schedule critical instructions before non-critical ones for the same reasons I just mentioned. And the goal is for that policy is to add contention only to non-critical instructions. Now we also want to evaluate how that works. They use the same workloads as before, and they have different architectures. They compare the performance degradation for 2-clustered 4-way issue architecture, for 4-clustered 2-way architecture, compared to unclustered architecture. And then they further compare the improvements against the heuristics you've seen before. So as you can see here, you have the different architectures and also the improvements over the baseline, which is the register dependence steering. They run it once with just the focus scheduling, and then with the focus scheduling and the dependence steering and the focused scheduling. And what you can see here is that for the unclustered architecture, there's a speed up of 7%, up to 7%, with an average of 3.5%. For the 2-cluster, we turn the slowdown from 7% to a slight speed up of 1%. And for the 4-cluster, you improve the degradation from 19% to only 6%. And what's also notable here is you can see that the yellow bar is very prominent. So the focused scheduling does most of the improvement, and the authors say that that's because the focused steering policy only comes to play when you have a tie, and that is not as often the case, whereas you apply the focused scheduling overall instructions. There's no conditions to apply that. And then the second evaluation you can see, which is against the heuristics, and they measure the speed up over no critical path prediction. So you can also see here that the token passing algorithm fares very well against the heuristics, and also for the Gulgle workload, which previously the oldest uncommitted, I think, or oldest unissued heuristic was better. You can see here now that with all playing together, the token passing algorithm works the most effective across all workloads. So let me conclude. The problem the authors tried to solve was that you have increasing parallelism in out-of-order execution, and that warranted critical path analysis. They tried to predict the global critical path of a program, and the challenge they had was that the previous analysis only considered data dependencies, And then if you want to do it in hardware, you only see a fraction of the code. So you have to figure out a way to predict the global critical path while only seeing a fraction. And they used the token passing algorithm to work around that. And you also saw that it works pretty nicely with the improved scheduling that improves CPU performance for up to 21%. And the prediction, which I didn't talk about, improved CPU performance by up to 5%. So that's it with the summary of the paper. Before I analyze the paper and we start the discussion, I want to give you a chance to ask questions about the understanding. So if there's something you didn't quite get, I'm happy to help you understand. Yep.
Sorry, only one thing. When you said that with this token passing algorithm, we establish only if the first node is on the critical path, is it right? Or we consider all the nodes we have gone through and also say, okay, also this could be on the critical path?
Yeah, that's a good question. So it's only for the node that the token is planted at. And you can mitigate that by planting multiple tokens at the same time. So you have more evaluation. But the reason that you only do it for the token, for the node that you planted the token at, is if you would do it for all the nodes on the path, you would have to buffer that path somehow, and that would cost additional hardware. And they don't want to get too expensive hardware-wise, so they just do it for the token, for the node that the token is planted at.
What I wasn't sure of when reading the papers, is the prediction done at runtime or before?
Yes, it's done at runtime. They do it in the processor, so they can do it at runtime. That was also what I had trouble understanding the first time. But basically, they just run through the program, and while it is running, they start making predictions about the criticality of the nodes.
But isn't the prediction based on forward passing the tokens?
Yes. I see where the confusion comes from. That's also what I had trouble with when reading it. It is forward passing, but the way I explained it is a bit different than it is actually done in the hardware. What happens in the hardware is that the last committed instruction is given to the predictor. And then the predictor looks at the last arriving edges for that instruction. And then it sees all the dependencies that are, and if there are nodes coming from the nodes, sorry, I keep confusing nodes and tokens. If there are tokens coming from these nodes, then that's the forward propagation. So they look, okay, this node creates a dependence. Does it have a token? And if there is a token at that node and it was last arriving, it is given to that instruction and it's written to the trainer. I have it in the backup slides. Can I find it now? No, let me show it later on. I can, or yeah, let's do it right now. Okay, yeah, that's the schematic in the paper. And you have the committed instruction here. And they give the instruction ID. And then what the processor also provides is the last arriving source node for the D, E, and C node of the instruction. And now you have the instruction that was just committed and also the last arriving, the last dependencies that were resolved. And in this token array, for each instruction, you have the information whether there is a token currently alive at a node of this instruction. So you have these nodes that are still in the token array because we've sized it to the reorder buffer. And then you read, as you can see here, you read all of the states those nodes are in, and then you can read whether a token is alive. And then in the next step, if there is a token that was in the D, E, or C node's last arriving source node, it is propagated to the token that was just committed.
Okay.
Yeah, it's a bit difficult to understand, but I'll also talk about that in the analysis.
Okay.
Okay.
Sorry, but one more question about
Yes.
this. Then I have the information about the last committed node, but the node already has committed. So the computation for that node, for that instruction is done, right?
Yes. Yes.
So with that information, how do I further predict for the rest? Because I don't see, if I only get the information about the already committed nodes, how do I improve performance
okay.
for future
Yeah,
scheduling?
so
That's
the idea
my
is that the instruction doesn't only get executed one single time. So you keep coming back to that instruction, and then the predictor writes the information it has to the array where it is stored, whether that instruction was deemed critical or not. And then when the next time the instruction comes up, the processor knows, okay, I've dealt with this before, it seems to be on the critical path, and now I can apply the improved policies for that node.
Okay, then it makes sense. Thanks a lot.
Yeah, my question is related to that. So you don't have to create the graph, or you do?
You don't. Yeah. Yes, you don't. You don't have to keep track of like chains of chains along the graph. The only thing you have to do is you have, and as I said, I'll come back to that in the analysis. But the only thing you have to do is read out the information from the processors about which operands produced a dependence, or about which nodes. As I showed previously, it's distinguished between D, E, and C node from the processor side. And I only have to know which of those nodes were last arriving for the instruction that was just committed. And then all I have to do is look up in the token array whether a token was alive at that node that was the last arriving for the instruction I'm looking at. So you could argue that you build a tiny graph for the node you're looking at, but it's immediately forgotten about. There's no saving of any graph structures in the hardware.
And you only store nodes, not edges in the...
Yes,
Oh,
correct.
yeah.
I only store nodes, and then the edges are implied when delivering the source nodes for the last arriving dependencies.
Okay.
Yeah, so just going back to questions, if I understand correctly, then basically the idea is to build up like a profile of how a program behaves on the CPU, and the CPU can use that to speed up the computation.
Yes. Yes.
Now, have they mentioned how it handles, for example, changing workloads, such as on a shared system where, for example, the CPU is swapping tasks? I assume that also some workloads would have, for example, a section of the program would have certain characteristics, and then a different one would have a different one.
Yeah, so they don't talk specifically about widely varying workloads. They use these 12 workloads. They don't really motivate why they use these workloads, but they probably just want to show that it works for different workloads. But in this case, I imagine what would happen is that at the start, there wouldn't be any improvement, but even if you only keep the program open for like 5 seconds, that's millions of cycles already, right? So there will be some prediction made by that time already.
And second of all, how do they choose the starting nodes? Is it randomly that they choose like instructions where to plant the tokens?
Yes. The heuristic they went with is that they just plant the token randomly. So at the start, obviously, all are available. So within the first 10 instructions, the tokens that are available are planted at random nodes.
Yeah, perfect. Thanks.
So, can you hear me? Yeah. Just from my understanding, this graph that becomes mostly unimportant when you start talking about tokens. But this graph that's built, you mentioned weights on the edges.
Yes.
What are these exactly? I'm not familiar with compilers, so I'm guessing it has something to do with that. But
yeah, it doesn't have to do anything with the compiler, and I also mentioned that you don't have to worry too much about the weights, basically, because for the simulation, you just observe the execution as it unfolds, and then you can see which nodes are, which edges are last arriving. So it doesn't matter specifically what the weight is, but more which instruction arrives last at which node. And that's also what enables the efficient implementation in hardware, because you don't have to know the weights. You just need to know which instruction or which node is the last to resolve its dependence for the node you're looking at. And then the weights are abstracted away, basically, because if it's the last arriving, it took the longest to get there. It was the heaviest weighted chain of instructions, and that makes it part of the critical path.
okay, so these weights are like a model of the latency.
Yeah. Oh, yeah. Sorry. Yeah, I did. Exactly. Yes. It's just it's an approximation for the latency that it takes to resolve the dependencies.
Okay, I see. Thank you. I think that's it. Thank you very much.
All right. Great. So now for the analysis, which I spoiled a bit when skipping through. Yeah, so the strengths of the paper. What's really great is that they're the first to kind of solve the problem of predicting a global critical path with using hardware, which is hard to imagine because you only see a fraction of the code in hardware, and they came up with a way to predict a global critical path. And then what's also great is once you have the critical path, once you know which instructions are producing or defining the overall runtime, there's lots of different optimizations you can make. So for every application, you can identify the critical path, you can identify also why it is critical, and then you can apply different optimizations for the critical instructions. And personally, also what I mentioned previously, what I found really nice is from the validation approach they used for their model is also the notion of the dominance of the critical path, which could also be used to just analyze your software, right? So you run this, you can see, okay, well, there's not that much reduction per latency I reduce. That means I have a near critical path, or if there's a lots of reduction, if the ratio is very high, near 1, you know that there is one chain of instructions that is very dominant for the critical path, and you can also use that knowledge to improve your software if you wanted to. And then for the weaknesses, the validation method I praised just now is actually apart from what I just said, is not. It's not easy to understand why they did it that way, or they sort of work around a few weaknesses. Mainly that it's not really sound what they do. What I didn't mention is that they had to work around a limitation of their simulation software, which was that the simulation software didn't allow for latencies of 0. So they had, before they decreased the latencies, they had to increase all latencies by 1. So they could later decrease it after they identified the critical path. And the problem with that is, if you identify all edge weights by 1, there's some funny stuff that can happen. For imagine if you, instance, if you imagine a critical path that's only comprised of 2 edges. They're really heavy, but it's only 2 edges. and then you increase the weights of all edges by 1, then another path, which is comprised of lots of edges, may now be critical because it got lots of ones added to the weight, while the critical path only got an additional weight of 2. So you might skew the actual critical path analysis. And they also don't talk about any solutions to this problem. They just omit it. And they also don't talk about any solid theoretical proof of why the model they came up with is sound. And then what led to a few understanding problems also for me is that the hardware implementation is pretty ambiguous. They have the schematic, which I showed you in the paper, but they don't exactly explain how you should read out the signals and how you should infer the last arriving information from the information the processor gives you. They just say that they expect that the last arriving rules can be implemented in hardware efficiently by reading out control signals. That's as far as they go regarding specific hardware implementation. And then also, I showed you the training parameters they used. They just use them. There's no motivation per se in the paper why they use these specific parameters, except for the propagation distance they talk about. And there's no analysis of how the predictor behaves if you change those parameters. Right. So let's start with the discussion, which I want to inspire with some points. Firstly, you've seen they expanded the compiler model with 2 additional nodes, the dispatch and the commit node. And that still doesn't capture all the dependencies. And for instance, cache line sharing, they mention, is not captured by that. And what that means is that that if you load memory, if you load an instruction, if you load data from the cache, then a whole cache line gets read out from the cache, and that might impact the runtime behavior of other instructions too, which is completely overlooked by this model. They say it's precise enough. We also see that it already works pretty well, but it's still not a complete model of the critical path. So yeah, you might come up with dependencies and nodes that would help capture the dependencies to add to the model. And then the training parameters I mentioned. The question is, how could we tweak the training parameters to increase performance or to adapt it to a specific use case? And the parameters they use to train, which could be tweaked, are the token propagation distance, the maximum number of tokens in flight, the hysteresis, the heuristics by which a node is deemed critical, and also the policy for planting tokens. And then lastly, I talked about the wide variety of applications for a critical path analysis. And I'm curious if you have any nice ideas what we could use it for. There are lots of papers like Mohammed said in the beginning that make use of that idea. You have a paper from a working group with Professor Mutlu that applied that idea to GPUs, and they introduced the notion of core criticality, which they measure by the warps that have outstanding memory requests over the total amount of warps in the core. So if that ratio is high and you have a lot of warps with outstanding memory requests, you could deem that core critical to the execution time because it doesn't tolerate a lot of additional memory requests. And then they come up with a memory scheduler that measures this criticality and improves runtime accordingly by considering the criticality of cores. Then another very, very interesting work is the optimizing cache prefetching paper I mentioned here, which does the same analysis, the critical path analysis. It's pretty similar to the model they used in this paper. And what they found out is that if you schedule cache accesses and prefetch data from the cache according to critical path analysis that you can completely eradicate the level 2 cache. They showed that it's not necessary anymore, that you only need the level 1 cache and the last level cache. And basically that it's enough to know which instructions are critical to the cache prefetching. And it doesn't hurt runtime if you eliminate the level 2 cache, expand the last level cache to further hide the hard drive dependence. I lost my train of thought, sorry. Yeah, so they found out that if you use criticality analysis, that you can get rid of an entire element of hardware. And then lastly, the focused value prediction was picked up by Intel recently, where they used critical path analysis too to improve their value prediction policies. And the idea here is that if you know which instructions are critical, you only predict those, because there's no use in predicting uncritical instructions, because in the best case, you gain nothing because they weren't defining the runtime in the first place. And in the worst case, you mispredict, and then you could increase the latency because you have to flush the pipeline. And they also show that you can improve the performance by quite a bit if you only predict critical instructions. So that's it from my part. And thank you very much for listening to my presentation. And now I'm curious what your thoughts are. Thanks.
Maybe about your point about the applications, I don't really see why, well, it should be applicable to any application you run. And as you said, the hardware cost is pretty low. So what I wanted to know is, maybe by chance you know it, as the paper was introduced 20 years ago, is it or was it applied in hardware, in general purpose hardware? Because the way I see it, I don't see a reason against it.
Mm-hmm. Yeah, that's a good question. I also was curious about that. And the paper itself has a lot of citations. So there's lots of different ideas on how to use that. But the way they describe their critical path model and predictor in hardware, I don't think that there's a lot of specific implementations like that, but there are a lot of different ideas of critical path analysis. For example, the GPU memory scheduler, that's a whole different idea of criticality, or at least it's a different way to estimate criticality. So they don't, so often it's not that they use this exact model, but they use the idea of criticality to improve scheduling and access requests. And the focused value prediction, for instance, that's a paper from Intel, and they tested it on their Skylake processors. So they were pretty happy with the results. So I figure they will also implement it.
But even if I used a different definition of criticality, I can still use the same proposed hardware accelerator, or the hardware they propose.
It depends, because, for example, in the to use the example of the GPU criticality thing again, is they don't do an analysis of like nodes of a chain of nodes, instruction nodes in the paper. They use the measure of criticality as the warps with outstanding memory requests over the ones that can already calculate, because there are no memory requests pending. So they don't analyze what the dependencies per se are, which instructions depend on which, but they analyze at runtime how many outstanding memory requests there are per core, and then they use that as a measure of criticality. So in that case, the predictor wouldn't do much because it's a completely different measure of criticality.
Okay, thanks a lot.
Can you maybe go back one slide? I think it was one. Yeah. So for optimizing cache prefetching, I was just wondering if you know, in case you read the paper, how did they do it with critical path prediction? How does it compare to other prefetching mechanisms that we have? That exist?
Yeah, so in this paper, I didn't read it as thoroughly as this paper, obviously, but they actually use a model that's pretty similar to the model in this paper. And they, I think what they do is they use a bit more hardware. They buffer the graph for a bit so they can do a dependence analysis over the graph. And then they basically predict which instruction needs cache access, and they prefetch it for critical instructions. So you only need to prefetch it if it's critical, because otherwise it wouldn't impact execution time that much. And the idea is then, if you have predicted that, you can get it to the level 1 cache, and you only have to hold the critical instruction. You can hold the critical data there, and if you bounce back to higher level caches, the uncritical data, it isn't as problematic because fetching those from the higher level caches isn't as costly to the overall execution time. And that's why they also conclude or say that you don't even need a second level cache, because once you sort by criticality, there's not need for that much hardware to save the data. But yeah, to answer your question, they use a model pretty similar to the one in this paper.
Okay, thanks.
So do they train continuously or only once in the beginning which path is critical or which nodes? Because this is closely related to memory latencies and the cache hierarchy, right? If they do it only once in the beginning, then it might be quite off, because once things are in the cache, the critical paths would be
Yes,
different.
so you're talking about the general idea or about a specific paper?
I think how they envision it in this paper, the one you're talking about.
In the cache prefetching?
No, and your paper.
In my paper.
Yes.
Yeah, so they are aware that if you have analysis at the beginning and then you start to optimize for that there are near critical paths with which start to emerge, which then dominate the execution time. So they also don't say specifically how you would do that, but they propose to do the analysis continuously. So for the hardware implementation, that would just mean you have the instruction passed by multiple times. You have different behaviors because of caching and, like you said, memory effects. So when the instruction comes again, the last arriving edges might be different. There might be no token. So the criticality prediction changes throughout the running of the program.
That makes sense.
All right. I think we need to stop now because there's another presentation. But thank you very much. Yes.
I think we need to stop the live streaming, right? Or are you fine with keeping the live stream on YouTube?
You hear me? Yes. I think it's fine.
Okay, we will keep it then. Great. And Rahul's going to introduce you and before you start.
Joel, can you hear me? Cool. So, hello everyone. I'm happy to introduce Cedric.
Slow down, we are not ready yet.
Oh, okay.
Oh, so you need. You can share this window, I think. Can't you just select it in Zoom?
Yeah, I mean, they don't see it yet.
So.
That's right, once. Now we should be able to.
Yeah, but they see the cameras here.
Right. Well, no. When you screen share, I mean, I can remove them for you or for the room, but on Zoom they shouldn't see. I cannot see my own mouse. That should be hopefully good.
Is everything fine on Zoom?
Yeah. Perfect. Can I introduce you, Cedric, now?
Yeah, you can.
Okay, so hi everyone. I'm really happy to introduce Cedric Casper. Cedric is in his 4th year of bachelor studies, and today Cedric is going to talk about Pythia. And as you will see, that this is a kind of a marriage between machine learning, reinforcement learning to be exact, and computer architecture. And I hope you'll all like it. So Cedric, go ahead.
So yes, welcome everybody. Today I will present a paper from 2021, so pretty recently, and it's about Pythia, sorry. What just happened? What is happening?
Stop sharing.
What the fuck?
Reshare. Yeah, that's okay. Which one would be better? Right now, it's the monitor. Can we stop the screen sharing? Do you think app would be better? No. It's not good. Okay. It doesn't flicker when you're not sharing.
If this doesn't work, that's bad.
Sure, can you internet?
Maybe we can open it on the browser and it's more works better there.
Let's just try again until it's flickering again.
Okay. Can you see it on Zoom? Nope.
No.
But they can start it flickering, I guess.
Yeah.
So how can you access it in the browser?
Yeah, I can't see the password, but yeah.
Yeah, okay.
Shouldn't. No, you don't. Yeah, okay. Everyone seen the email now? if they can still see the screen. I can't. Okay, now I need to share again. Oh, why is it? It's clicking out. Let's hope it doesn't flicker again. Okay, I start again. So I'm presenting the paper from 2021 today about Pythia, a customizable hardware prefetching framework using online reinforcement learning. So first, I will talk about prefetching and the reinforcement learning background, then Pythia itself, and the performance analysis. So prefetchers are here to predict data that will be needed in the future by looking typically at a single program feature and finding access pattern in it. Now the paper proposes Pythia and uses it in conjunction with reinforcement learning. So prefetching is needed because DRAM latency now is still nowadays a critical bottleneck, and unfortunately, spatial locality is provided from the data itself and can be used to increase performance. The problem is that there are also irregular patterns when coming from the processor, and finding these is difficult, inaccurate, and very hardware intensive. Now, there are a couple solutions around this latency. For example, we could just reduce it, but that's very expensive. Then we can tolerate the latency by, for example, multi-threading or out-of-order execution, and maybe what you just presented. And we can also hide the latency, what we are doing today with caching and prefetching. Now, there are many different types of prefetchers nowadays. It started all with the simple prefetcher that just prefetched the next line or with a constant stride. Then a bit more complicated models are called cache block address-based stride prefetchers. They learn different strides and assign them to prefetch buckets to prefetch the data there and keep it stored in there. Then a widely used variant of these are called stream buffers, and curiously all the buckets are used with stride 1. So that works is quite fascinating because we would think there are many different strides. Then there is also locality-based prefetching, which uses tracking entities to find patterns in the access, to learn pattern in the accesses. And when they repeat, they just repeat the pattern again on prefetching. Now for Pythia, we want it to be adaptive to access pattern switches. For example, if the processor has a context switch, the accesses will change. And for the first time in prefetching, we want to encompass system feedback from, for example, the bandwidth usage that is currently, from the bandwidth that is currently used. And also we want our model to be parametrical, to change its behavior without a need to change the hardware itself, because that's how it is done today. All of this can be done by using reinforcement learning, which is a different form of machine learning in itself. So unlike in supervised learning, we don't need training data in advance with reinforcement learning, but we can still train our model in advance. We can choose between using offline learning, which means training it before deployment, and online learning, which means the model learns from itself on the job. Now, this is typically done in reinforcement learning with using an agent and the environment. So the agent lives in the environment and gets a state from it, and then performs actions inside the environment and receives a reward for these actions. Now, these rewards are then used to adjust its Q values, which represent the expected result you can get from these specific actions. And this is what drives the model to do what it needs to do. Now in our case, our agent is a prefetcher, and the environment is a processor and memory system. Now let's look at the state. So we define the state as a k-dimensional vector of features. Now the features are extracted from control flow informations and data flow informations from the demands coming from the processor. Now per feature, to make it even more reliable, we don't need both in a feature. We can choose if we have both of them and only one, for example, a data flow component. But we will see later on how this is chosen. Now, what is the action? So our agent, our prefetcher, gets a demand address and then selects an offset within the current physical page. With the recently used microarchitectures and cache sizes, this leads to an action range from -63 and +63. But this is way too much, so we will prune that later on. Inside this list, there is the 0. So we want there to be the 0 because we want our prefetcher to be able to do a null action, to do nothing, to do no prefetch at all. Now the only thing that remains is the reward. And this is what defines the objective of PTI itself. So here we encompass 2 metrics. First, we want the prefetches to be useful. And secondly, we want the system feedback to be encompassed here. This is what drives the model to be more efficient. So many different kinds of rewards get created and assigned at different times. So we have the best one is first here, accurate and timely. So it means we have done an accurate request and the data has come back on time before it was requested again. Then we have accurate and late and out of physical page because we only want to prefetch inside the physical page. Then there is a reward for no prefetching, and here it begins to diverge a bit because we want our model to do no prefetching, but we don't want it to do all the time. If we gave it a positive score, it would probably just do no prefetching at all. So we slightly punish it when it does a prefetch, but not as much as, for example, if it does an incorrect prefetch. And here we see that we have 2 different kinds for no prefetch and inaccurate prefetches. So this is due to the system feedback I talked about. Here it is the memory bandwidth usage. So for example, we do an inaccurate prefetch. It is much worse when we have high bandwidth memory bandwidth usage. And it is not so bad if we have low memory bandwidth usage. But it is flipped with the no prefetching because we want to encourage no prefetching when there is high usage of memory bandwidth. Now, with all that defined, we can look at Pythia's design itself. So Pythia has 2 major components. We have the Q value store and the evaluation queue. The Q value store contains all the values that are used to choose the best action from the given state. We will look at this in a moment. The evaluation queue contains all the recently done actions by PTI itself. So each entry contains of the state action pair that created the demand. It contains a field bit determining whether the data that was requested got back from the memory and was written into cache. And also it has a space for the reward that gets assigned to it. So for every demand that comes to the prefetcher, we first of all look at the evaluation queue if you already have a request for that address in there. If we know we have done an accurate prediction and can assign the specific reward depending on the field bit if it is timely or late. Then we extract, regardless if we find anything in the evaluation queue, we extract the state vector and look up in the Q value store. How this is done efficiently, we'll look in a moment because it is the heart of Pythia itself, sorry. The action that gets returned from this will then be given to the memory controller and simultaneously be stored inside the evaluation queue again. Now here we can also assign rewards, the immediate ones. So if we do a no prefetching and an out of physical page prefetch, we see that they will never be changed later on. So we can immediately assign these to the entry inside the evaluation queue. And finally, by adding something to the evaluation queue, the first element gets evicted because it is a first in, first out queue. And when evicting the value, we write back and update the queue values with the received award. If we haven't received the award until now, we know that we have done an inaccurate prediction because it was never asked for again. And we can then assign the last couple of rewards. So in stage 1, 5, and 6, we have rewards that get assigned. So now let's look at the queue value store itself. In here we have for every state action pair, we have a queue value that gets stored, and it represents the expected value for this action and that state we are currently in. So the paper proposes a specialized 2D table instead of a specifically normally used neural net-based storage method. So the problem with that is, for example, firstly, the table size, because it corresponds exponentially to the number of features we use. And therefore, to come around this, we will use a bit of hashing. And also we need this access to be fast because it is directly tied to the prediction latency of the whole prefetcher. Now, inside the store, we have for every feature, we get a vault. And inside this vault, there are planes. And the planes then are used to encode with multiple overlapping hash functions what's called tile encoding. Now, the tile encoding works like follows. You have, for example, a 10 by 10 square of values, and the hash functions map all these values to just one single value. In our case, a partial Q value. Now, this allows for sharing of the partial Q values for similar features. And we have multiple planes to allow the opposite of widely different features because we don't want them to share the same values. Now the hash functions reduce the size quite drastically, but we still have the problem. We index a two-dimensional table with only one dimension. So we need to access the table for all possible actions that the prefetcher can do and find out the maximum. For this, the paper proposes a pipeline, and this is done by iterating over all possible actions and keeping track at the end of an overall maximum Q value and action that is found and then returned as the chosen action. Now, this pipeline drastically decreases the critical path as pipelining typically does. Therefore, we can increase the prediction latency overall by keeping an area overhead to the minimum. Now, finally, for the design, as we are in machine learning, we have lots of hyperparameters. So to fix these, the paper uses what's called state space exploration. It's basically brute forcing them. So we create all possible pairs of control flow and data flow components for our features. Then we create, from these pairs, we create any one, any two, and any three combinations, which is then hundreds of combinations, and run all of them and choose the best one. Then again, we do the same for our action list pruning. So we take all possibilities of removing one element from it and running all these possibilities, choosing the one that has the least impact on performance, and doing this over and over again until we only have 16 actions left. And finally, we have the tuning configurations, and in there are also the reward numbers. And these are done by, again, creating thousands of configurations with uniform grid search and running all of these and choosing the best one. Now, interestingly, when doing all of this, we can see that the features chosen are PC plus delta, which is a control flow and a data flow combined. And the second feature is just a data flow component, the sequence of the last 4 deltas. And again, the very shortened action list. So now that we have pretty much finished the design, we can look at its performance. So PyThea is tested against multiple state-of-the-art prefetchers, including Bingo, which was the most compared to in the paper. Now we can see that although we are using a machine learning model, the size of the model itself stays pretty reasonable. So the first metric we will look at is the coverage and overprediction. So coverage means that for every demand from the processor that falls through L1 cache, we see whether the processor has predicted that request and already delivered the data. And here we want the black bar to be at 100% because then it means we have predicted every request. Also, we don't want our predictor to just predict everything. So this is what called overprediction, because we predict something that is never used. And we want the gray bar then to be very low. So here we see that PyThea constantly has the highest coverage over the competition and having the lowest overpredictions. Next, we look at the speed up that brings with it, because speed up is quite different from coverage. So we see that we tested in a single core and a 4-core system, because the difference is because we have taken memory bandwidth into consideration and we want to see the effect of that. As you can see on the average bar on the right from you, that PyThea consistently has the highest speed, the black bar, has the highest speed up, and this leads to a 3.5% speed up in a single core system and 7% speed up in a multi-core system, again, due to the bandwidth consideration, because in multi-core system, the bandwidth gets used more by the different cores. Now, any questions so far? Where is the microphone? Who has the microphone?
When you were talking about the rewards that are given for a specific request, when you said that we make an inaccurate prefetch and we differentiate those rewards, those negative rewards between low and high bandwidth usage, you mean that that specific request use a large portion of the bandwidth that is available, or that
No.
In general in that context the program has to use a large amount of bandwidth, and so the request per se doesn't use this a large amount, but it wastes it wastes part of the bandwidth that is needed.
No, it's not the request itself that creates a lot of bandwidth. It's the system as a whole has a limited bandwidth available, and there is a metric inside the processor that just states how much is used of it, and therefore we distinguish with a threshold if it is high or low. But each request basically just stays at the same size of data, so it doesn't make any difference if one request is low or high. It makes in the summation if it is low or high. That's why it is better in 4-core system, because each core takes into consideration what the other cores are doing via the bandwidth usage.
And is there a reason because we choose to have just to use a threshold, so to divide the bandwidth usage between low and high, instead of maybe making a continuum of possible rewards I could give based on the percentage, for example, of the bandwidth that is used?
You could do that, I suppose, but it is done here. It's machine learning. You can choose most of the things. So they chose to use 2 rewards for low and high. I'd say if you have too many different kinds of reward, it gets tedious when applying those rewards inside the architecture, in the physical architecture itself. So if you have only 2 or maybe 3, 4 distinguished numbers, it's easier to implement those.
Okay.
We meet halfway.
I think that you mentioned that, if I remember correctly, Q values, you mentioned that typically you would, sorry, I have this written down.
You mean typically is
That
a
they
neural
would be
net?
you mentioned something about them being accessed with a neural network typically. Right?
Yeah, it's you can think of a neural net theoretically as just a table. It's quite crazy, but you with a table you just have an input dimension and you get a value out. And with a neural net, it's quite actually the same. It's a lot of calculation in between, but you just get, you have the input vector that is same as, for example, if you have a 2D table, you have 2D input vector, and then you get one value out of it at the end. So that's why you can use a table and the neural net for machine learning and reinforcement learning in particular here.
Okay.
Does that answer your question?
Kind of. So just wondering how this looks like. Can I imagine a table of Q values? And then the index will be spit out by a neural network? Or am I misunderstanding?
No, it's more of an abstraction. You don't have an actual table if you have a neural net.
So just the
it's
value
the weights. The
spit out
weights
is the
in
Q
a
value.
way are the table, but
I
you
see.
have to multiply and sum them up and use the functions and so on. It's like if you have a neural net and you pre-computed it for every possible input and stored this in a table.
Yep.
So those are the two ways you can see it.
Okay, cool. Didn't know that's how it works. And also one more question. So is Pythia the only prefetcher that considers system bandwidth? Are there other examples of this?
So the paper states that until now, most prefetchers don't use any system feedback. And they chose memory bandwidth as their system feedback. You can choose others, but they chose only one for now. And yeah, that's quite the novelty in the industry, I say.
Cool, thank you.
I would like to make a comment here.
Okay.
Well, Pythia is not the only prefetcher which uses memory bandwidth feedback as a to incorporate memory bandwidth feedback in its prefetch decision. There are other prefetchers, but typically what happens is that normally these system level feedbacks are designed as an add-on to the existing prefetching algorithm. So basically you have a prefetching algorithm that understands what pattern you want to prefetch. And then on top of this basic algorithm, you have some sort of, let's say, feedback mechanism that uses bandwidth information or pollution information to throttle the prefetching or maybe make prefetcher aggressive in some other cases also. But what Pythia basically tries to make a case for is that you should not consider this bandwidth level or any other feedback mechanisms as an add-on to the underlying algorithm. But what you can do is you can make the algorithm itself aware of these feedbacks. So basically, you should not consider these feedbacks as a second-class citizen of the design choice, but it should be the first-class citizen and as equally important as the other features that we are using. So in that sense, Pythia is unique, let's say, but definitely it's not the only one that uses system level feedback information. And if you want to read more, you can also read for FDP, the feedback directed prefetching, and then there are other works also that this paper has already mentioned. So yeah.
But yeah, the paper doesn't really state anything in that regard, only that it wants to use that more than others, if there are any. So yeah. Any other questions?
Yeah, I think the two questions are kind of related. I had a feeling. So the reason why they are using the lookup table, I guess that's because of speed.
Size.
And size.
Yeah, because you have to do a lot of, neural net have to be a lot, you need to have a complete engine that runs a neural net that sums and multiplies and uses activation functions.
But so if you have like a sufficiently large model, wouldn't there be so many combinations of inputs that storing this entire huge lookup table would actually take up more space than having this compressed model based on weight and computing it on the fly? I think this is maybe like a discussion points for
we can look at it
where
later.
you have to look up and make sure.
Yeah, you need to evaluate and see whether, example, they use hashing either to bring the table size down again. So maybe it was an argument in the beginning, but then it got flipped because they used hash tile encoding and so on and so on. But I'd say it's less, but I will come back to that in the conclusion, because what they did with the store is quite unique. So it's not just a typical neural net. So that's very different than what many others use.
Yeah, thanks.
Just a quick questions about the numbers and the results to get a feeling for the field of prefetching. Are those results good? Is improving by 3 or 7% like groundbreaking, or just okay in improving prefetchers?
I'd say, yeah, that's what I also have as a weakness of the paper, because it doesn't state what's good or how to improve even further and so on, but we'll come to that. I'd say in a single core, I'd say it's not groundbreaking, but in multi-core it is quite good, because especially they do another test where they constrain the bandwidth manually, and there you have an increase of up to 17%. That's quite a lot then.
I've got a question about the prefetch action list. So I understood correctly that you do some training or testing in advance, and then you've got this pruned action list, right?
What do you mean?
Which
one comes first? Is that your question?
What did you just say?
What comes first? The first, I had 3 different. These ones, you mean?
Yes, exactly. And then I've got this pruned list, right?
Yeah, the 16 at the end.
Yes, exactly. And is that list adapted at runtime? Or
no, that's fixed in beginning. That's fixed in the design in the hardware itself.
And those are my offsets for which I can prefetch from, right?
Yes.
Because what I'm wondering about is, isn't this extremely limiting? Because if something in the state changes slightly, then what do I do then?
I thought the same, but I think most of the time you don't need all possibilities. You only deleted the ones that had the least impact on performance. So I'd say if, for example, 64 values would have been beneficial, they would have used them. But I don't know the word in German. Erstaunt.
Astonished.
I was astonished too that the list got down to so few values.
Okay.
Because
And I remember correctly that in the paper they don't explain why.
No, they don't explain why they have
just,
so.
We learned this and this seems to be the best. So,
Yeah. The
okay.
problem is the bigger the action list, the longer the pipeline takes to spit out the values. So there's a trade-off there because you want to have as few. The list should be as small as possible to gain a speed up, but you also want to have correctness and useful results. So it's a trade-off there. Let's see.
Okay, thanks a lot.
Oh, can you hear me? Yeah. Is there some kind of insight to be gained from this result? For example, I see that sure, we have a whole bunch of parameters. We got some good values for the parameters that makes that gives the best performance for these parameters. But does the selection of these parameters give us some kind of insight into the problem itself? For example, so to set these parameters to these values means that we're exploiting some kind of like something in the problem, or do we understand more about the nature of this problem?
No, unfortunately, I'd say no, not a lot.
Yeah,
that's the beauty of, or not so beauty of machine learning, because you don't know how it works, you just know it works most of the time. And that's also a weakness of the paper. It doesn't have any theoretical analysis to why it works, just that it works.
Makes sense. Thanks.
Are there any questions on Zoom? Okay, so then I will go on to the strengths of the paper first. Oh. So I'd say the idea that is presented in the paper is quite simple and very well executed. And the paper presents multiple levels of details, especially on the Q-value store and so on the parts that are implemented in hardware. Also, the paper has a lot of self-analysis and testing that's gone into it. As we've seen with the hyperparameters, there's a lot of work that's gone into this. But again, we'll come to the weakness later. Also, what's funny is that they give an example usage and installation at the end, so you could use it today in your PC if you have Verilog. But yeah. Then there are a couple weaknesses. For example, in the beginning, there's a lot of repetition and arguing the same two arguments over and over again. For example, that we finally use system feedback in the first order and so on. And then we have again the typical machine learning problem that we only know it works, not how. Yeah, and this is reflected in that we need a lot of brute forcing here to find those hyperparameters. And I'd say this must have been quite a struggle, but the paper doesn't report any struggle at all. And also because of this machine learning problem, we have no theoretical analysis to why it works, and also no future improvements, because how do you improve it? Just try again. Now let's come to the discussion. I have a few short questions for you here. What do you think? Are there any security vulnerabilities with using prefetching as reinforcement learning? The one thing I can think of is that, for example, a hacker could make the model learn something wacky and bad and therefore bring performance of the whole system down. But that's not really a security risk, more a performance risk. Then also are prefetchers even needed in the future, because near and in-memory processing is coming. So we want to move less data around. And the data we are still moving around will get more erratic and more irregular. So prefetchers will have an even harder time. And then again, we had it in a presentation 2 weeks ago or last week, no, 2 weeks ago. Is this innovative or explorative? Because throwing a machine learning at the problem, I'd say, is not really innovative. But then again, the Q-value store with its specialized 2D version and the pipeline that is used to make it efficient has taken a lot of effort to make and is quite unique itself. Also, the promise of using all different kinds of metrics that can be quite easily adapted into it makes it more unique as well. So thank you for listening, and let's start the discussion.
So about the last point, innovation instead of exploration, and just throwing a machine learning algorithm at prefetching, and also about this machine learning algorithm being treated as a black box that's not explainable, that you don't really know how it works. But is it really that complex? I mean, you have rewards for certain states. This isn't a huge neural network where you come to a decision, but you have no idea how you came to it. You took some paths, you did some weird stuff. This seems pretty clear, actually. And as far as innovation goes, there was this whole talk about this prefetching mechanism, a core idea of it being this feedback that you get from the system. It's no longer an add-on, but it's a core idea. It seems actually very innovative, doesn't it?
That's what I said too, that the store and the idea behind it is innovative, but using machine learning itself is not really, because that's done everywhere, I'd say, in the last years.
But is it in prefetching, for example? Do we have?
Yes, there are other machine learning
perception,
approaches.
right?
Perception. There's a perceptron filtering prefetcher that uses a standard prefetching idea and then adds a neural net perceptron that decides whether the prefetch was good or not. But that's a simple approach, and here it is completely done with machine learning from the ground up.
Yeah.
What was the other part? What you said?
I guess I like the idea very much.
So. Yeah, I like it too. It's simple and great executed. So, but is it really innovative because you just like it?
It's not innovative because I like it. I think there are a lot of points that make it innovative.
Yeah, that's what I said too. Yeah. So it's a mix of both, I'd say. The idea of using machine learning is not innovative, but using the system feedback again is quite, and the implementation into hardware is, let's say, at least unique. Yeah.
I'll stay here for a second longer. I see that just blindly slapping machine learning onto a problem doesn't leave a good taste in the mouth, let's say that way. But this is a nice reinforcement learning model. Not again, maybe I don't need to repeat the same point again. Not a huge black box, a very explainable machine learning model. I don't know. I feel like this. I see no issue with using machine learning here, especially with all of the considerations about efficiently implementing hardware. And so as far as the last point goes,
but innovation, exploration is not always bad as well. So machine learning, it works obviously, and it's better than everything else we have at the moment, apparently. So it was worth it at all. But the idea of using machine learning, I'd say, is not really innovative in itself. Everything else is, yeah. So it's a mix, I'd say, but it's just an opinion.
Okay, yes, same here. Just an opinion. Thank you.
So what I'm wondering is if we're talking about exploration, what the dimensions of the exploration would be. Do we learn something about the hardware and how we should use it? Or would it be, could we learn maybe something about the software, how we should optimize it so the prefetcher works better, for example, or the other way around, how to further improve the hardware?
You mean innovation versus exploration?
No, I just mean in the space of exploration. When we're talking about, okay, now we want to, we have this work here that examines what's going on or tries to improve what's going on. And then you said, now maybe you want to learn something from that improvements we made. And then in what space would we learn something? Did we learn something about the hardware and how we should tweak it to perform better? Or is there maybe also a component where we learn something about the software and how it could be improved to make memory handling easier?
So software is not regarded at all in the paper.
Okay.
So it's just about using a machine learning algorithm with ideas of using multiple metrics in it, and then how to implement this in hardware efficiently.
Okay.
So what you can learn from it is that, for example, the features that were chosen are quite unique. No, not unique, but are a bit interesting, let's say at least. But again, you don't really know why they are chosen. It's just they work the best. And it's funny, but it's cool that it works, but that's the machine learning in a nutshell.
Okay, so you would say there's limited amounts of exploration we can do based on that work.
You can explore all the possibilities.
Mm-hmm.
In state-space exploration, they do explore all the possibilities. But really reasoning why they were chosen is quite hard. Especially, you can look at the Q values in the store that were chosen for it, but that doesn't really say anything. Again, with normal neural nets, you can look at the weight matrices, but they're mostly just noise and they work.
Okay, yeah.
So it's saying something about a neural net is really hard.
All right, thanks.
Maybe about the second point.
Yeah.
I would say yes, because especially processing using memory, and I also think processing new memory are restricted to simpler instructions. So we still have our main processing unit, and even if transfer between both gets less frequent, if it's still the bottleneck, or if it then gets the bottleneck, then we still need the prefetching to accelerate the travel of the data that can't be processed in using our new memory to get it to the main processing unit. So I would say yes, prefetches are still needed.
But then again, you would agree that they will have a harder time.
What they will?
They will have a harder time because the access patterns will get more irregular and erratic. There will be less data movement, and because there is less data movement, there is also less periodic data movement, and therefore the prefetcher will have a harder time.
Yeah, but still, if there's less frequent movement, if the movement that needs to happen is the bottleneck, then why don't prefetch it?
And yeah, I agree. We will need prefetching, but prefetching will have it harder, don't you say?
But if we process in memory, then we have the great benefit that we can overlap those those computations in benefit with the prefetching even better than maybe nowadays, where it's overlapped with computations in the processing unit. So I wouldn't say for sure that it will have a harder time.
Yeah, but then the speed up comes from the memory processing, not from the prefetcher itself.
Yeah, but still, if we wouldn't have the prefetcher and the data that would need to be prefetched becomes the bottleneck, but then we need a prefetcher because then our whole processing in memory acceleration, it doesn't help if those movements get the bottleneck of the system.
I agree, yeah. So I'd say, that's why I asked the question, if I'd say we will need prefetchers as long as there is cache and the latency problem. But the problem is I'd say they will have a harder time when there is more data processed in the memory, because if there is less data moved overall, it is likely that it is the irregular data that will be needed in the processor, not the regular data, because the regular data can be processed in memory.
No, that's not true.
Isn't
What can be processed in memory depends on the instruction you execute, because and not on the pattern in which you would access the data.
Yes, but for example, if you need to load an entire matrix into cache or into processor, then instead of you doing it in memory, the process of loading it is really regular.
Yes,
and if you don't need to.
But if you can't execute it in memory because you need to perform a complex instruction, which you, at least at the moment, if I'm correct, only more basic operations can be done in memory, then you still need to bring it into the caches. So it doesn't depend on the access pattern, it depends on the instruction. So it's still necessary if the instruction is complex.
Instructions generate the access patterns. The program that is running, for example, if it is a loop, generates the same access pattern over and over again.
But the question is what happens inside the loop? What's the operation on the data inside the loop?
Yes.
And if this instruction is complex and need to be performed in the main processing unit with the complex hardware, then you still need to move the data there because you just can't perform the instruction inside the loop in memory. That's my point. Maybe now it's a little clearer. But
so we just need the main processor is just there to coordinate the other smaller units, or just send the instructions to the memory itself to do the operating there. You still need probably the prefetch for some functions that can't be really done in memory, but I'd say it will become less if you do more in memory.
But I don't disagree with that. Maybe it's just, I guess still with your point, the point was that with, for example, UpMem, I just repeated for Zoom, you can perform, it's Turing complete, so you can perform any instruction, but like if it takes several cycles to execute the instruction there, because the logic is not perfect for the instruction, then there's a trade-off, and maybe again you need to bring it in the main processing. That's just my point of view about this.
Yeah, but then again, in-memory processing is not there yet. It's not really as efficient as in some cases it may be more efficient, but overall it's not that efficient now. But again, this is a question for the future, where everything is possible.
Yes.
Is anybody else something to say? Okay, then thank you for attending and listening to me.
So maybe before we conclude, can you hear me?
Yes.
Okay, great. Maybe I'll make a couple of comments. I don't want to spend a lot of time, but I want to make sure I think maybe some things are clear. So thanks for the presentations. I think these were very good, and clearly this paper was focused on core design, right? This week we were focused on core design, and we talked about two different ideas in core design. One is very recent, one is very old, let's say. And I think there were a couple of questions. The first one was basically, did this first paper like influence things? It definitely had a lot of influence in academic world. It's not clear. First of all, I think the criticism of the paper is reasonable, meaning the hardware design is not very clear. And the hardware design is not as, let's say, easy as the paper makes it out to be, I think, because it overlooks a lot of issues in the first one. But the contribution of the critical path prediction idea and a token-based algorithm is quite interesting, certainly, and that's had a lot of influence. It certainly influenced our work, as the first presenter mentioned, but there's also other work like predicting the critical path in a multi-thread application that we have also done. How do you identify the bottlenecking threads and how do you accelerate them? It is another form of critical path prediction. So I think this, let's say, token-based prediction mechanism may have a lot of overheads, but there may be other ways of estimating the critical path as opposed to trying to perfectly model it with some high hardware costs this token-based prediction mechanism may incur. And other works like future works actually focused on simpler ways of predicting the critical path of single-threaded or multi-threaded programs. Another issue, I think, is this maybe the first paper did not look into memory as much, because it was written at a time when memory bottlenecks were getting a lot worse, and it became a lot worse after that. So I think looking at these critical path issues with a proper memory model and understanding of memory in mind becomes a lot more interesting as well. So if you look at the paper, the modeling of memory is very crude, right? They model a lot in the processor, but the modeling of memory is 100 cycles, let's say, which is not realistic. And certainly memory is a lot more complicated than that. Okay, moving on to the second paper, I guess very quickly. I think there was a lot of discussion. I think we've got somewhat maybe, what should I say, that rat-holed in this innovation versus exploration thing. I don't understand quite what's really meant. So I think if there's insight into applying machine learning to a new problem in a new way, an insightful way that shows that machine learning actually works for that problem, then I think that's innovation, basically, right? If it's just like you take machine learning and don't provide any insight and apply it to a problem, then maybe that's not innovation, okay. But this paper does a lot more than that, actually. It tries to also reason about the features a little bit. Maybe Rahul can mention that as well. But so I think not every application of machine learning to some problem we cannot label that as not innovation in the end, because it takes a lot of work actually to make a machine learning algorithm work in a particular context, especially if it's reinforcement learning, right? Reinforcement learning actually is much more sophisticated, let's say, and a much more general model than neural networks. Right now, a lot of people are working on neural networks, and they are definitely black boxes. Reinforcement learning is also a black box, but there's more, let's say, reasoning that goes into it, right? Because it's not, you have to define the reward function, you have to decide the state features, and the state features, for example, are not as random as maybe the discussion kind of hinted at. It's more based on the experience of the designer and a feature selection methodology. So yeah, I think it's good to evaluate the machine learning ideas that way. And clearly, this is not the first work on prefetching, nor first application of machine learning on prefetching, but it's an insightful application of reinforcement learning into prefetching. And there was another question, which was actually a very good question that was not discussed as much. Are these improvements significant? So I would say two things. So the improvements are actually quite significant in the multi-core domain. So if you look at the paper with 12-core execution, the improvements are on the order of 10 to 20%, which is significant because all processors today are multi-core processors. The single core processor results are in the paper, in my opinion, just to make the comparisons and analysis easy. But today, nobody really runs single core applications, let's say. I mean, it happens, but it's not as much. So it's really important to evaluate the multi-core context, and 10 to 20% on average is quite significant, because this gets amplified across many, many different processors, right? So maybe the improvements are not like 10x, 100x that you may see with processing in memory, but the changes are also not as large. You don't change the model of the system. So it's important to think about it in context. And also the improvements are on top of the best prior work. That's also important to think about. It's not based on a weak baseline, let's say. Okay, I think there's more to talk about here. That the discussion was on in-memory, near-memory processing can go further. Maybe I'll give my little bit over here before we end. But I think there's certainly a need for examination of prefetching within the context of more memory-centric computers, like in-memory, near-memory computers, because yes, there will be need for prefetching, partially due to the reasons that were mentioned, but partially because memory latencies are still high, even if you're in memory. And if you can potentially prefetch data in memory to a near memory processor that's operating near memory, you can still overlap the latency of memory. So it's good to keep in mind that memory latencies don't necessarily become significantly lower with near memory processing, because you still need to access large DRAM arrays, for example, and you can potentially use prefetching inside the near memory processor to make things still faster. What near memory processing buys you is it eliminates the data movement overhead. It eliminates some of the latency, but it doesn't eliminate all of the latency, clearly. So there's a topic, there's more to investigate in this direction. And I think in general, the topic of using reinforcement learning for system design with new insight brought into it is actually a very good direction going into the future. We'll see more and more of that. Even though initially we may not be able to perfectly explain it, over time, hopefully we will explain things better. And that's a general problem with machine learning, not just these specific works, right? Explainability in neural networks is not great today. Reinforcement learning, there's more effort in that direction, but it's also not perfect today. Okay, I wanted to make these comments before we end. I don't have anything else, but if Rahul or Mohammed have something, they can either say something or end it. Thanks.
Yeah, I'll add one more thing, that this in the paper we do we do talk about how to interpret the results, right? And though it's not the as Professor Mutlu also suggested, though it's not the best form of interpreting the results, but we do have some sort of intuition that this this entire infrastructure literally learns the correct offset to prefetch from, right? So if you look into the deeper sections of the result, you will see the Q value as the Q value saturates over time, right? And then you can see that it quite literally selects and favors one offset than the other because of the Q value stays higher. And if you go and then look into the program, why that Q value is getting higher and higher, it's actually the program is making the memory accesses on the same path. So yeah, so in this sense, we can actually talk about not being a full black box, but we can have the confidence that this is indeed working and it's learning the correct program behavior in that sense. But still, there is a lot of work to do to even think about how to, let's say, systematically explore the state space, as well as make it autonomous in that sense also. Like even if we don't provide the, let's say, expert intuition on selecting the state features, but then can the machine also learn the best state feature on the fly? Yeah, that's what I wanted to add. Thanks, Cedric.
Okay, have a nice day.
All right, thanks everyone. So we came to the end of the lecture. Don't forget to take the quizzes, they are already up. Thank you so much for the two presentations and for the mentors. Take care and see you next week. Bye-bye.